k nearest neighbor. So this first we are going to study what is instance-based learning. Instance-based learning, the idea behind is very simple. We just store all the training samples in a database. If you remember, when the algorithms what we have discussed so far is we are using those training samples to come up with some hypothesis that simulates or that actually approximates the true function. So in instance based learning, it is also kind of a learning, but what we generally do here, we whatever the data set we are having, like what are the training examples we are having, we don't do anything and we just store it into some database. For an example, I have this kind of a database. For example, this is my input xi could be a vector, right? It could have a lot of n components or d components, and fi is the value, like what is the label of that particular x. So f will tell, the function will tell that what is the label of that. So if I have this kind of a same sample, well, I can store all these into a database, and somebody comes and asks me what is the value of this let's say xq. So for what I can do in a very simple manner, I will try to find out what are the nearest neighbors of this given query point in my training data set. Wherever I will find out, like let's say k nearest neighbors or n nearest neighbor, k will depend upon, k is a constant. For example, I will say I will try to find out my approximate number by using top 10, using 10 nearest neighbors or 5 nearest neighbors. So every time somebody comes and asks me what is the label of this query xq, I will find out my k nearest neighbors and check what is the label of those nearest neighbors are having. The if they are, like for example, they may have more than one label. In that case, I will do the majority. I will count which label is actually major in these 10 labels. For example, let's say I will take 3 nearest neighbor. So this is my key query point, and in my data set I will find out that these are the 3 points. These are the three samples which is nearest to xq. So for example, first is having positive sample, first is having positive label, second is having negative label, and the third is having positive label. Now when I found out that among the three nearest neighbor of my query point, there are two positive and one negative. The majority of the points are belong to the positive class. Therefore what I will do, I will assign my label to this query point xq as positive label. This is very simple manner. So in k nearest neighbor, there are two things. There could be two things. One is my label could be discrete, or they could be real valued. So for example, this is a case of discrete. Let's say I may have three kind of labels. One is positive, other is negative, and third is cross. So there are three kind of label. And somebody gives me a query point and asks me what is the label according to k nearest neighbor of this. So I will go and look into my database, and let's say I'm using 10 nearest neighbor algorithm. So in 10 nearest neighbor algorithm, I will find out what are the 10 nearest. So let's say these are the 10 nearest points that I find here. So these are the 10 nearest points that I found here. And among these 10 nearest points, I see that this class, X class, wins the majority. Therefore, I will assign the label to this query point as X. So it is very simple. So this is a case discrete. This is a discrete case. Okay. By label you mean output of the hypothesis, right? So there is one question, by label you mean output of hypothesis. So hypothesis we say when we learn some function using a training data set. So I cannot say this is the label of a hypothesis. It is a label by a true function. I don't know true function what it is, but this is the label of a true function. I shouldn't say it's a hypothesis, because hypothesis is when we learn using those data set. Right. Hypothesis is for when you learn some function from an available data set. So we shouldn't say that this is the label of a hypothesis. It is a label of a true function. Okay, so one question, what if there are five positive levels and five negative levels? How do we categorize in such a case? So this is a good question, but what happens generally when we decide what is the value of k? In case of binary, we always try to take k as a odd number. So when we use k as an odd number, then this possibility of getting equal number of positive and negative class will not happen, right? But if let's say there is some restriction that you have to take some even number as k labels, then you can. This is a tie. This is a case of tie. You can break it up on depend upon your algorithm. So another question is it nearest neighbor means the value of xi which is plus k or minus k from. No. So the nearest neighbor means, for an example, this is my two-dimensional data point. So this is my x vector is, let's say x is having two dimensions, x1 and x2. So my input vector is x, which is having two component, x1 and x2, and my label, let's say y is equals to negative and positive. So when I draw these things into a two-dimensional place, so how can I do this? Let's say this axis belongs to x1 and this axis belongs to x2. Now these are some points that I plot my class labels, and this is that what I got, right? So this is there. So let's say this is when I plot my labels on two-dimensional graph. So this is what I got. Now somebody comes and asks me that for a given input point, let's say this is an input point. Now this is my xq. So this is my xq. So this is my xq. This one cross. So somebody asked me what should be the label of this new point here. Then what I can do, I because this is a Euclidean space, right? So I can find out what is the nearest neighbor of this query point. So let's say I have to find four nearest neighbor of this query point. So I will take these four nearest point according to the distance. So when I take the distance of this point with this point, this point, with this point, this point, with my query point, and this point with my query point, they are the only 4 points that are nearest in my data set. Now when I take all these 4 points, I will find out, I will see what is the majority of the class labels here. So I see that there are two positive class labels and two negative. So this is a tie here. So I can break this tie by taking any of the class label. And if could be like there could be another positive also, then in the five nearest neighbor algorithm, I will take five nearest neighbor and find out which is the majority. So here three is the positive class labels and two are the negative class labels. So I will assign this xq as my positive class label in case of five nearest neighbors. So I hope you got it. Distance is the Euclidean distance. Yes. So here distance, I mean to when you are saying that you have to find out what is the nearest neighbor. Nearest neighbor means that you have to find out which in Euclidean space which is near in the terms of distance, right? Okay, I hope that you got this point now. So there are two more. I was saying there are two things. That one is discrete case, what I am discussing. So this is what I have discussed so far is a discrete case. In that case, this is the formula. This is a fancy way of writing the same thing what I was telling in the algorithm. It is like, for an example, V is having positive label and negative label, right? Let's say this is V is having positive and negative. So for when I take positive, I check my sample positive. What is the nearest neighbor? Fxi is the nearest neighbor, nearest point of my query point, right? So there are k query points, say k nearest neighbors. So I will check first for positive. So this is a delta function. So delta function means when these both are equal, when a b equals to 1, a b equals to 1 only when a equals to b, and a if a is not equals to b, then it is equals to 0. So this is the case when a equals to b, and this is the case when a is not equals to b. So this is an indicator function. So when the class label is equal with the nearest label, then it counts 1. So for all the labels, it counts 1 for positive, which are so in the nearest neighbor, let's say there are 3 positive and 2 negative points. So this indicator function will get high for 3 points. For this, for positive, for this, for this. So I will get 1 plus 1 plus 1 equals to 3 in the case of positive. And when I take V as a negative, so this will get high for twice for these 2 negative points. So the 1 plus 1 equals to 2. So when V equals to positive, then the value will be 3. When V equals to negative, the value will be 2. So it's straightforward. You have seen so many times these kind of algorithm, this type of expression in previous slides. So this is a case of what we have discussed so far is a discrete case. What happens if somebody asks you that, well, let's say there are the discontinuous values. So in the nearest neighbor, now somebody say that this x1, there are x2, this is x3, and this is my query point xq. So let's say that now these x are not having a discrete labels, they have continuous label. For an example, this x1 is having 2 value, this x2 is having 3 value, and this x3 is having again 2 value. So what is the value that at query point q will have? So what you will do, you just divide it, you just add all these things and divide it by 3. So this is what you will get. So 2 plus 2 equals to 4, 7. 7 divided by 3, whatever you will get, 3 point something, 2 point something, right? So this is how you will get the in the case of the continuous function. Okay. So when to consider nearest neighbor, so the instance is mapped to a point in RD here, what do you mean to say? That you are able to calculate the Euclidean distance of a given point for any 2 points in a data set. So that's why we are saying that the instance is mapped to a point in Rn. So if we can map our instances to Rn, then only we can calculate the Euclidean distance. And if we can calculate the Euclidean distance only when then only we can find out which are the nearest neighbors, like k nearest neighbors or any nearest neighbors. So the ideally the attribute should be less than 20 here. I will let you know why it is should be less than 20. So lots of training data is required. If the more we have a training data, the better we will have accuracy. Advantage, training is very fast. You can see from here that we don't have to do anything. When every time somebody comes you and gives you a training data set, you just store it. Store it in a very efficient way so that you can retrieve each and every object. So here there is a practical issues like how you will store your data set. The more efficiently you will store it and you can retrieve it, the better your time complexity is. So learn complex target function. In this case of k nearest neighbor, it is not always that you learn some linear function or some quadratic function. You can learn any kind of function. The decision boundary could be very non-linear. We don't have to lose any information because we are using every data set that is given to you. So what does this point mean? So generally what happens when you have some data set, you just break the data set into training data set and testing data set. And when you come up with some hypothesis using training data set, you will test your hypothesis using that stressed data set. So what I'm saying, for example, somebody comes to you and give you some data set. What you do, you just break it to 80% and 20%. You use this 80% for your hypothesis training, right? When you come up with some hypothesis, sometimes you want to check how good this hypothesis is. Then you use this 20% data to find out whether this is actually giving the same results what my true data function is giving. So if this is giving to my true result, then that's fine. So here you see that that we generally break our data set into some proportion like 80% or 20%. But in case of k nearest neighbor, we save our 100% data at a time, 100% data, and we use this for training. Now my new query point will come. I just need to find out which are the nearest neighbor, right? So how we learn complex target function here different from other learning algorithm, I will let you know. So I have some two, three slides that will have you a clear intuition how you can learn complex for target functions here. So disadvantage is so training is very fast, right? But at the time of labeling, like at the time of query, somebody asks you what is the label of this XQ, then you need to find out k nearest neighbor, and k nearest neighbor is not an easy task here. So you have to iterate through you have 1 million data points in your data set. So for you have to calculate 1 million Euclidean distances, and then you need to sort those Euclidean distances, and then you have to take top 3 or top n number. So it is a very big process. It will take time. So it is that disadvantage is at the query time it is very slow, easily fooled by irrelevant attributes. So let's say there are 20 attributes and only 22 attributes are having a information regarding that label point, and 18 are irrelevant, just a waste. So if those 18 points are irrelevant, then when you calculate the Euclidean distance, those 18 or 18 attribute will also play a role. And it may happen those 18 attributes which are not giving any significant information for the label, but when you calculate Euclidean distance, they may result in a greater distances what it could not be. For an example, what I'm saying. What I'm saying, let's say this is X and it is having 3 attributes, X1, X2, and X3, and only this X1 is important to know the class label. For an example, my Y label is this. So every time I get 1, 2, 3, I get positive, and every time I get 5 to 6, 5, 6, 7, I get negative. 1, 9, 8, I get positive, and if I get 5, 11, 17, I get negative. So let's say this is the only attribute which is important to find, which is having a relevant information, and these two attributes don't have any relevant information. But when I calculate my Euclidean distance, so these 2 points also play a role, because they also help me to decide what is the distance from this point to this point. Now if they are irrelevant, and it may happen because of these irrelevant attribute, my closest point could not be that which should be there. I hope that so an example, these two should be very nearest because they are having the equal data points, equal data label. So these 2 points should have because these 2 points have equal class label, positive and positive. So they should be very near to each other in a Euclidean space. But when I plot it into a 3-dimensional space, what I see that this X1 is 1, right? But X2 is 2, let's say, and X3 is 3. X3 is 3. So somewhere it will come here. So this point will come somewhere here. So this point is this point. Now when I plot this point, so this one is 1 again, X1 is 1, this is 9. So on X2, at first when it was 2, now at this time it is 9. So I will go here up to 9, and when I will be here when it is 9. and it will be 8 in the third dimension. So when I go to up vertically 8, so it will somewhere here. So these 2 points, those are having same labels, which are positive and positive. They should be near to each other because the relevant attribute is only x1. But when you're plotting with x2 and x3, then you see that they are lying very far from each other in this three-dimension Euclidean space. But if somebody asked, somebody gave me relevant information, no, you shouldn't use x2 and x3 because they are not relevant. They are not giving any information regarding these class labels. Then what you can do, you can only plot this x1. So when you plot only x1, what happens? So this is 1, this is 2, this is 3, and let's say up to 5. Up to 5, this is 3, this is 4, this is 5. So when you plot this first point, it will come on to x1 is equals to 1. When you plot this point x, so it is 5, it comes here. Let's say I'm denoting it by circle. When you plot this point again, third point, it comes again on 1. So now you can see they are actually lying on each other now, where they are very near to each other. But when you were using x2 as 3 also, which was not actually having a relevant information, and you are plotting them into a three-dimensional space, they are lying very far from each other. So that's what I mean to say, you can easily fool by relevant attributes. Okay, so what is the question here? Sir, if there are a million points and a new point comes in, do we have to check distance from all million points? Yes, sir. That's why I am saying that it is very slow at carry point. Okay. So the other question is, these could be classified by decision tree because x1 is more important, but xn and x in knn x1, x2, x3 are treated equally. So I don't want to compare it here with decision trees, but you will see that both are having advantage and disadvantages over each other, right? So if you can also say that this is not as good as the neural networks. You can also say it is not good as logistic regression. So there are hell lot of ways to compare it with some other algorithms. So right now I don't want to go into that discussion which one is better than that. But yeah, you are correct that if you in this case if you plot decision trees that will definitely behave more decently and accurately in comparison to this KNN. Yeah, you are correct for this case. Okay, so in two-dimensional play space, this is called as Voronoi diagram. Voronoi diagram means to say that if I will plot my decision boundary, for an example, in the single case, when I want to in a case of one nearest neighbor means to say whichever the closest point is there, I will assign that class label of my closest point to my query point. So if I want to find out my decision boundary, what will happen? There are four, 5 points are there. So and I am using one nearest neighbor algorithm. So when I use one nearest algorithm, for example, my query point is this. So when this is my query point, the distance of this point is smaller than the distance of this point and this point. Let's say this is 1, this is 1, and this is point 0.8. So what this hexagon is saying, that in this hexagon, anywhere you take a point, that point is always less than the distance from other points. So this is why it is showing some kind of a boundary or region. That region will always classify the label. That region always classify the correct query point to the label of that point which is actually exist in this region. For an example, what I mean to say here, this let's say this could be a positive. So if somebody say that this is a query point, because this is a decision region here, so and my query point falls into this region, it means this must have a class label positive. I'm talking about one nearest neighbor here, right? This is one nearest neighbor diagram. So if you calculate the distance from here, it is always shorter than the distance from this point and to this point. So likewise, if you plot these regions for one nearest neighbor, you will say that this the Venn diagram of this is this. If you say that what is the decision for this query point, and the decision boundary for this query point is this. So in this case, this class label will be positive, and sorry, this class label will be negative because the majority in this decision region is negative. So let's see what is the linear, how KNN behave in respect to linear regression. So let's take an example of a linear model in a classification context. My x is input variable having two components or attributes x1 and x2, and my output class label y is a binary variable having values 0 and 1. So there are 100 points in each of the two classes. So there are altogether 200 points, 100 point in each classes. One class is orange and other class is blue. When I code it in my computer, I denote blue by 0 and 1 by orange. Now if I plot these 100 points in two-dimensional space, so I will see that this is my in two-dimensional space I plotted these 200 points. So these are 200 points. When I plotted them, these are here, right? So orange are represented by 1 and blue are represented by 0. Somebody asked me to find out like what is the best line that you can find out for this thing case. So the best line is this, and it is saying that every time you the linear regression case would be x transpose w and minus 0.5 equals to 0. This is the line what I will get. So if this point is greater than 0.5, so if x transpose w is greater than 0.5, I will fall to it in this region. If x transpose w is less than 0.5, I will fall into this region. So this is, if this is the case in linear regression, the the linear boundary is this, and I cannot do better than this if it is a case of linear regression. So let's take another two scenarios. In one scenario, I am saying that I am generating these labels by two Gaussian mixture model. See, this is scenario one. This is scenario one. I am saying that I am generating these class labels by two Gaussian mixture model. So this Gaussian mixture model is generating, so let's say orange points, and this Gaussian mixture is generating, let's say, blue points. Now if these are the two Gaussian mixture models and they are generating these 2 points, and these Gaussian mixture are bivariate Gaussian. Bivariate Gaussian means it is the points they are generating are actually lie in two-dimensional plane. So the point, let's say this Gaussian model will generate will be, let's say, x1, and x1 will have two component. For example, this is point P1, so it will have two component x1 comma x2. So every point that is generated by these these Gaussians are bivariate. The second scenario is that there are 10 different Gaussians. The training data in each class came from a mixture of 10 low variance Gaussians with individual mean. Okay. So there are two classes again. Let's say class 1 is having, in class 1 there are 10 Gaussian mixture models, 10 different Gaussian mixture models, right? And in class B also, or class blue also, there are 10 different Gaussian mixture models, and each Gaussian mixture model is generating some points. Let's say orange, 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 here blue, blue, here blue again, blue, blue, blue. So this is for blue, this is for orange. So here you can say that there are 10 mixture models for blue and 10 mixture models for orange, and each mixture model is generating some points. So here density is higher near mean. So here density is higher near mean for this Gaussian. Here density is higher near mean. Density higher means that the orange points are near more here in near to the mean. Similarly, the blue points are more near to the mean of these Gaussians. So I have generated my points by two ways. First way is there are only two Gaussian mixture models. One Gaussian mixture model is generating my orange point, and other more Gaussian mixture is generating blue point. If I find out what is the decision, if I need to classify these two class labels or these orange and blue points, what is the best hypothesis I can take? Because these are the two Gaussian mixture models only, with I can best define them with a linear hypothesis, because these are two Gaussian mixture. So my linear hypothesis is the best what I can do in case of linear hypothesis. And but if I will take if these are the two Gaussian mixture models and they are overlapping, let's say, it could happen. For an example, in this case, I draw them like differently, but what could be the case? Let's say they could overlap also. For this is the first Gaussian mixture model and this is the second Gaussian mixture model. Now they are not overlapping. So this is generating some orange point and this is generating, let's say, some blue point, lower one. So this is generating some blue point and this is generating some orange point. So now this is the area where we have a maximum error. But if we want to classify them for using a linear boundary, so the best line that I can draw from here to here is this. Still I can find out the optimal line which classify them. But in this case, if let's say if this is the case and these are overlapping, so when this is the 10 Gaussian mixture models for blue, for orange, let's say, and these are the 10 Gaussian mixture model for, let's say, blue. So these are the 10 Gaussian mixture model for blue. Now somebody asked me to find out what is the decision linear boundary. Can I find the optimal linear boundary using linear regression? So if then it is very hard to find out. Let's say this could be a linear boundary, or this could be a linear boundary, or this could be a linear boundary. So in scenario 2, if I will trying to fit my data set using a linear decision boundary, that is not a good choice here. So if I will use my KNN here, if I will use my KNN here, then the best choice that I will get, then the linear decision boundary is quite good. So here you can say that I am actually able to draw my decision surface as non-linear rather than using linear. So for an example, this is when I take 15 nearest neighbor point, and this region is actually belongs to blue point here, and this region belong. When I take 15 nearest point for towards this point, this is orange. So every time I take a decision regions for 15 nearest neighbors, so this is the point. These are the regions where every time the point falls here, then it always classify as blue point. For an example, precisely what I'm saying here. Oh my God, what precisely I'm saying here is, for an example, this is my cherry point. Let's say. So if somebody says that you have to classify using 15 nearest neighbor, so 15 nearest neighbor, let's say these are the 15 nearest neighbor. These are the 15 nearest neighbor. So here these are the 15 nearest neighbor, and out of these 15 nearest neighbor, the majority is winning by blue. So that's why the color is blue here. The color is blue here, and the color is orange because in this region, if you have a query point here and you take 15 nearest neighbor, every time you take a 15 nearest neighbor, the orange will win the majority. That's why this color is orange here. So if you have a 15 years neighbor algorithm, then you can see that you able, then it is doing a much better job when you were doing it with the linear classification. So actually, from this example, what I'm trying to say, that KNN actually can classify, can draw non-linear boundaries. When the data is not linearly separable, then also KNN can do a better job, right? So but it is also having some disadvantages. For an example, somebody says that I will, what happens when I will use you one nearest neighbor? So this is a case of overfitting. So overfitting means, for an example, I'm not generalizing it. Every time I see my query point and the first point I find out, I will assign my query point that same label what my nearest point is having. So this is not a generalized case. So this is the case of overfitting in case of one nearest neighbor. So how do we use KNN to draw the boundary? I understood. How do we use KNN to draw the boundary? I understood. This is a question actually. How do we use KNN to draw the boundary? I understood. How to predict a label from the known data set, but able to understand the way to predict the boundary. Is it not okay to have multiple boundaries like in this slide? So this is, yeah, this is multiple boundaries. You don't say this is, these are the multiple boundaries. This is actually a decision surface which is actually classifying one class of label to one region and the other class of label to another region. So decision surfaces can be continuous or they cannot be continuous. In this case, for example, one nearest neighbor, there are a lot of islands also. Yeah, here you can see that this is a case of a very complex function or very non-linear boundary, I would say. So this is case of I don't get the question, previous question. I don't know what is that. How to use KNN to draw a boundary? I told you how to draw a boundary, right? How to predict a label from the known data set. That also I told you. How to predict label from the known data set, but not able to understand the way to predict the boundaries. So predict the boundaries. This is not your job to predict the boundaries. So what I am saying here, like for what I am saying here, prediction of label is understood, right? So this is not your job to. mm So what I am saying that why these are points are blue, why this region is shaded as blue and why this region is shaded as orange. So the point I am saying, if you will take a query point here, right, and you will take 15 nearest neighbor points here. So if you take 15 nearest point here, then according to this color, the blue point will win the race. The blue color or the blue class labels will win the race. So if you go very take a slowly step, take a small step and find out what are the 15 nearest neighbor, and according to the color of the majority class you will assign this blue. So likewise, when you draw this boundary, you will find that this is a non-linear region here. There are few blue islands in orange region. If my query point is near that island, then it may lead to the wrong classification. So what this is a question. There are few blue islands in a orange region. If my query point is near that island, then it may lead to a wrong classification. So it depends upon what KNN you are using. Obviously, because this is I am saying it is a case of overfitting. It is not generalizing. There may be a lot of time there are possibilities when you are misclassifying your error. There will be an error in classification. So it is fine. It depends upon what nearest neighbor you are using. Okay. So this is distance weighted KNN. So what is distance weighted KNN? Rather than using only the nearest neighbor, then what I am here saying, then you can weight your class label with the weight of your distance also. For an example, what I am saying that this is there are two class labels here. Let's say this is my query point here, and there are two class labels. This is positive class label and this is negative class label. If I find out that this is the nearest one, so I should give more weight to this class label, and this is the farthest one. in comparison to this class label, I should give less weight or less importance, I would say. I will give less importance to this class label. So this importance term, I am calculating it by the term by using a distance, Euclidean distance of a query point by the class label. The more the distance is from the query point of a class label is, the less weight it get. So the distance I am calculating from a query point to some point that I'm using for my k nearest neighbor. If the distance is very large, then 1 upon very large is very small, right? So it means the weight is inversely proportional to the distance. I am now what I am doing here, just see for this discrete case first. What I am saying that let's say the positive is very near. This, let's say I'm taking V as positive first time. So my first class label x1 is positive and the weight is very near. So let's say the weight is only 0.1. So 1 upon 0.1 is 1 upon 0.1 is 10. So weight will get 10 here. And let's say when I take my second point for positive, second point, the distance is let's say 100. So 1 upon 100 will be 0.001. So in that case my weight will be 0.001. So now I have two class label, one with the weight of 10 and other class label one with the weight of 001. In that case my distance was only 0.1 and in that case my point distance was 100. So depend upon what is the distance from my current query point to a point in a database, I will take a calculate a Euclidean distance and inverse it. The larger distance would be, the less weight I will get. It is quite intuitive also, right? So this is what, how does the weight help us? So this is a question, how does the weight help us? I think so the weight help us says that you always give more importance to those which are near rather than to those which are farther, because the nearer point is having a larger weight. So it is saying, let's say you have two data points plus positive and negative and you are giving equal weightage to them. So when you are giving equal weightage to them, let's say 0.5 and 0.5, so finally you will conclude that out of these 2 points, 50% the probability will give to the positive point and 50% chances will be the, or 0.5 probability will be the given to the negative point. But if I say that weight given to the plus will be 0.8 and weight given to the negative will be 0.2. Now I am saying that 80% it is chances are there that this is a positive class label and 20% this is a negative class label. So weight is a statistical term, sir. You should understand why, how weight is playing role here. So another question, why do we need decision boundary since xq or query point can be classified from nearest neighbor? So sir, for your information, I would say that every time you take some k nearest neighbor point or algorithm, k nearest neighbor algorithm, every algorithm in the learning world, machine learning world, always draw a decision boundary, right? So you should understand what is decision boundary. So for example, every time you take any algorithm, that will always draw a decision boundary for your intuition. So then only the point fall on one side will belong to one class and the point fall onto the other side of a boundary belongs to the other class. So this is not a genuine question, why do we need a decision boundary? We actually don't need a decision boundary. Decision boundary comes with algorithm. So the question is another question. So distance was enough to judge that, right? Yes, distance is enough to judge that, right? So these are not my algorithm. These are given by Mr. So and so, and this is a distance weighted algorithm. What I am saying, I am giving a weight to the labels according to the distance, and this is how we are coming up, right? So now it makes sense to use all training examples instead of K. So this is a very beautiful point here. Now I say that am having, like, say, rather than using k nearest neighbor point, I can use my whole data set. So let's say this is my whole data set. So this is positive, this is negative, this is positive, this is negative, positive, negative, positive, and I come up with my query point here. So this is my query point. So according to this query point, what I would say, this distance is smaller. I give weight according to this distance. I give weight according to this distance. So I give weight according to this distance, and similarly I give weight according to the every point in the space, and I will consider every point here according to the distance, and I will put this into this formula according to the weight, and I will find out what is my class label. When I do this thing, I am using all my training data set to find out what is the class label according to the weighted nearest neighbor algorithm. This is known as Shepard's method. So curse of dimensionality I have already explained you in a bit way when I was drawing it into a when I was telling you what are irrelevant attributes and what are relevant attributes. So curse of dimensionality means the more dimension we are having, the Euclidean space or distance will get broader and broader. So if I say that I am saying that I am having a one-dimensional space. Let's say this is a line. So in one-dimensional space, my nearest neighbor of, let's say, these are 1 and 1. So this point is 1 and this is 2. So the nearest the distance between these 2 points is 1 only. When I plot these two things on this on two-dimensional space, let's say this is 0 1 and this is 1 0. So the distance between them will get bigger and bigger. When I put these 2 points in a three-dimensional space, let's say one point fall here, another point will fall here. So the distance between these two distance get bigger and bigger. So this is called a good curse of dimensionality. So what we actually want to do here in k nearest neighbor, we just want to find out what are my relevant attributes, and I will mostly set my irrelevant attributes to 0. So for an example, this is my x1, x2, and x3. So x1 is important, a relevant attribute, and x2 and x3 are not relevant attributes. In that case, I will give I will make this x2 and x3 vanished from my data set. So I will multiply them with 0 and finally left out with x1. And now based on my x1, I will find out my k nearest neighbor and give my class labels. So this is locally weighted regression. Okay, I will take a little break here and I will continue then afterwards.